Go. Hello and welcome back to Calculus 3, section 15.5 on directional derivatives and gradient. We learned about partial derivatives. Partial derivative in respect to x is taken in the x direction. Partial derivative with respect to y is taken in the y direction. And those were the only two directions defined so far. What if I want to take the derivative in any direction? Well, if I want to take the derivative in any direction, then I need to specify the direction. And we know that the best way to specify the direction is to use the unit vector, because the magnitude of the unit vector is 1. It will not change the value of the derivative. However, it will give it a direction. So, to find the directional derivative, we are going to define it through the dot product. We are going to have a definition using the good old limit. And then we are going to have a formula that will actually calculate these things, because you don't want to mess with the limit, right? So let f be differentiable at AB, that's the point, and let u hat, given as u1, u2, be a unit vector in xy plane. The directional derivative of f at the point AB in the direction of u is, and now we have this formula, the derivative in direction of u of f at AB is given by the limit h goes to 0 of f of a plus h u1 comma b plus h u2 minus f of ab divided by h. So this is the definition to calculate the derivative, but as I mentioned, this is not the way that we calculate the derivative, because it's a limit. We use the formula which says that the directional derivative in u direction of f at AB is going to be the dot product of fx computed at AB, comma fy. So these are the partial derivatives computed at AB, dotted with the unit vector u1, u2. So this is the way to compute directional derivative. And as I have to point out, guys, over here, that most of your grade suffers because you are not paying attention to have the unit vector there. So if I give you a vector 3, 4, that's not a unit vector. 3, 4 is a vector that has magnitude of 5. That's not a unit. So you have to change that vector into 3/5 and 4/5 and then you can go and do your directional derivative. So directional derivative is going to give you a derivative in any direction you want. That direction is going to be given by the vector u, but it is your job first, before you do anything else, to make sure that this thing there is the unit vector. So here we go. Make sure that this is a unit vector. Otherwise, doom. The problem will be wrong. So, find du f(16) whatever for f of xy equal 3xy squared minus 2x plus 1. In the direction of u equals 3, 4. So standard problem, you just plow through this. Well, first off, immediately you say not a unit vector. That is a huge thing. You have to deal with this first and then deal with the rest. So we go and say u hat is vector u divided by the magnitude of u, which is vector 3, 4 divided by 3, 4, 5 triangle, right? So that's a 5, gives you 3/5, 4/5. Yay. Now you can go and find your partial derivative fx. Fx is going to be 3y squared minus 2. Now that's fx. What I need in a formula is fx calculated at AB, and AB, as you can see, is 1/6. So from here I calculate fx at 1/6, and that is going to be 3, who picked this number? 6 squared minus 2. That's 36 times 3 minus 2. 36 times 3, was that 90, 108, 106 altogether, right? Then we find fy. Fy is 6xy, and we need fy 1/6 because we are looking for the derivative at 0.16, and that is going to be 6 times 1 times 6, which is 36. Great. So now the directional derivative in the u direction for f at 1/6 is going to be the dot product between vector 106, 36 dotted with the vector 3/5 and 4/5. And that is going to give us, remember, this is the dot product, so we're not getting a vector, we are getting a value, and that's the value of the slope that you are looking for, right? It's a derivative. So it better be a scalar quantity. And the dot product does give us a scalar quantity. So 106 times 3, that's a 318 over 5, plus 36 times 4, 120, 144 over 5. Common denominator is already there. So we have 462 divided by 5. And that's the value of the derivative. As to interpreting it, just give me 10 minutes. So we now have the complete picture. You can find the partial derivative in respect to x, which will measure the change, right? The slope of the tangent line, it will measure the change in x direction. We have partial derivative of y, measures again the change in the y direction. All of the tangent lines you can get slopes, right? And now, to complete the story, if you want to go in any direction, you can figure out using directional derivative, but you have to provide the direction in which you are going to look at, and that direction is going to be given by the vector u, which you must scale down to unit vector in order for this to work. Yes?
If you were asked for the directional derivative in a direction that's tangent to the way the direction it was changing, that yields 0. So like if a function is going this way and changing in that direction, and you were asked in this direction, you get 0, right?
Because of dot product, yes.
It's a dot product. Okay. That's what
Well, it's coming up, but great that you already sniffed it out. But yes, before we give the meaning and actually reinforce what you asked, we're going to quickly define gradient because we already used it. We're just going to give it a name now. So this is definition gradient. Gradient of f of xy is simply the vector of partial derivatives. So that's all it is. Vector of partial derivatives. We already had this in our definition for du. We said we had a and b instead of x and y. So gradient, this symbol, well, I'm going to box this, and then I'm going to point to this symbol. This symbol is read as del. So you would say del. It is not, this symbol is read as change when you have the triangle regular way. It's capital D in Greek, delta. But the upside down triangle is called the gradient, and it's a vector of partial derivatives. If you have ever seen any of those fancy formulas, maybe in Maxwell equations and so on, or you've seen some of the partial differential equations and so on, you have seen this symbol floating about. If nothing, you at least seen it on Iron Man. Yeah. All right. So now this definition is because now we have this, we can redefine du FAB as del f AB dotted with the vector u. So that's a vector formula now. We do have it up there in what I call an exploded version. But this is nice way, concise way to memorize the formula for directional derivative as gradient times the unit vector. That's the most concise way to put all of this. So now it's time to talk about the gradient, and then we'll see that, right, we can calculate stuff. So this is really cool. So, theorem, directions of change. Let f be differentiable at point AB, so that's our domain, with del f not 0. Number 1. F has its maximum rate of increase at AB in the direction of the gradient. Del f AB, the rate of change is magnitude of the gradient. So let's understand this. So what I have here is a surface that has the domain on the floor. I pick up an AB xy point on the floor, which shoots straight up to give me some z somewhere on the surface. So we can plot the entire surface by going to each AB point on the floor in our domain, calculating z value in f of xy to come up with the surface. Then we pick some AB that we're interested in, which produces a single z value on the top of the surface. Now, if you pick any value on top of the surface, any point on the top of the surface, there is going to be, at that point, a direction in which you are going to go the steepest way up, right? Rock climbing. And the steepest way down, nose diving, right? So any point on the surface, that you have is going to have the maximum rate of increase, which means the steepest way up and the steepest way down. And those will be measured by, well, now we're going to write number 2 for the maximum rate of decrease, which is, as I said, the nosedive, the fastest way down from. Sometimes these directions are desirable. Sometimes you want to avoid them at all costs. Let's say you are in the army, for instance, and you need to drive a vehicle on a terrain. You are looking at the map, right? You all know that there is a certain level of the slope on which you cannot drive. The vehicle is going to flip or whatever. So you definitely are not looking for the steepest way up and the steepest way down. You will be looking for directions that are not so extreme. So you need to be able to calculate. Now, obviously, you can have devices in your vehicle that measure the tilt and everything, and obviously this being programmed in, this is where you come in, right? It will be real-time computing and telling you, okay, we're not going to go this way, we're going this way because, right, this is, you're trying to avoid the steepest either increase or decrease. In some cases, steepest increase is what you are looking for, which is rock climbing, right? Because you're not going to rock climb on a flat surface. Number 2, F has its max rate of decrease at AB in the direction of negative del with the rate of negative absolute value del f at AB. And here is the question you had earlier. The directional derivative is 0 in any direction orthogonal to the gradient. The directional derivative is 0 in any direction orthogonal to del f AB. So each one of these dels is supposed to have an arrow above because those are all vectors of partial derivatives, so they should have arrows. So I'm going to now just write that we can also have gradient in 3D in R3, and that's going to be del f of A, B, C, x, y, z, which is the vector of partial derivative of respect to x, x, y, z, partial derivative x, y, z, and partial derivative x, y, z. So that will be gradient in 3D. Directional derivatives, we did that. Let's take a look at one of the direction of steepest ascent and descent. Great. Here, perfect. 36 has some trig. Can never go wrong with trig. So fxy, the surface, is given to us as 2 sine of 2x minus 3y. This is going to be some wavy surface. And point of interest is 0 pi. We're looking for the steepest ascent and descent. Find directions of steepest ascent and descent. Well, we start with figuring out our partial derivatives of xy. So partial derivative for x, if it's x, then this 2 will come outside, so it becomes 4 cosine of 2x minus 3y. And fy is going to kick out negative 3, so negative 6 cosine of 2x minus 3y. Those are our partial derivatives. Now we compute the gradient, which is you just put these together in a vector. So gradient of f at xy is going to be 4 cosine 2x minus 3y, comma, negative 6 cosine 2x minus 3y. So steepest ascent is going to be in the direction of positive gradient. So I need to find gradient f at 0 pi, and that's going to be 4 cosine of negative 3 pi, comma negative 6 cosine of negative 3 pi. When I plug in 0, it kills x's, and then pi for y becomes negative 3 pi. So now we calculate this as 0 pi. They're only asking for the direction. They did not ask for the value of it. You just find. Now cosine of negative 3 pi. What's the value? Is the same as cosine of 3 pi. What's the value of 3 pi? Very good. So that's 4 times negative 1, and then negative 6 times negative 1 to give us the steepest ascent at 0 pi to be negative 4, 6. This is a vector. It shows the direction, right? If you are moving in this direction on the surface that is provided to you, this will be the steepest, hardest way to go up in terms of this one. And now descent is just going to be the negative of this, so you don't have to recompute anything, you just change the signs. So 4 negative 6 is going to be the fastest way down. So steepest ascent is this, and the steepest descent is this one. They're going to have a problem with the square root. They're going to have a problem with e to the negative x squared over 2 minus y squared over 2. So it's just going to make it annoying with derivatives, so that you have to review all of your derivatives from Calc 1. There's a problem with ln of 1 plus x squared plus 2y squared. You know, it's the procedure and the concept of all of this is, as you can see, what it is. The rest is figuring out the problems. For directional derivative, what is the one thing that messes up most of the students? Anyone? Paid attention? Unit vector, exactly. Your u has to be a unit vector. Please, please, please. U has to be a unit vector.
So if they asked for the direction of steepest ascent and steepest descent, would they want it in a unit vector form, or that's fine?
No, just this is fine.
Okay.
And then you would be multiplying this with the unit vector to find the derivative if you want to go in some other direction. But this is the direction of steepest ascent and steepest descent at the point on the surface. So the fastest way up, fastest way down. The slope of the tangent line in this direction would be simply the magnitude of this. So you can find also the rate as square root of negative 4 squared plus 6 squared equals to, here, just do it. That's that. Bye. Hope you're not disappointed.